I'm delighted and would like to introduce Roald Koudenburg, who's going to be talking on formalizing size in formal category theory. So please, Roald, whenever you're ready.
Thanks a lot, Tim, and also thanks Tim and Dries for organizing this workshop. It's very nice to have double categories. So in this talk, we'll take a double categorical approach to formal category theory. We'll do formal category theory in double categories and also more generalized kinds of double categories. And we'll focus on formalizing the classical Yoneda embedding and also formalizing classical notions of size, like small categories and locally small categories. And especially with these formal notions of size, we will see some advantages over well, the traditional approach to formal category theory that's using mostly two categories. So here's the plan of this talk. Motivation will be unifying these two notions, one of a sub-object classifier of topos theory and the other one classical Yoneda embeddings. This won't be a very deep result, but it might be nice to see how you can make it precise, and also making it precise leads us to the right kind of double categorical setting. So that is that of augmented virtual double category. So that's a double categorical setting in which you don't have composites of horizontal morphisms, and also you don't have horizontal units. So that's what we'll work in. Then in those augmented virtual double categories, we'll look briefly at Cartesian cells and co-Cartesian cells. Cartesian cells define restrictions of horizontal morphisms. Co-Cartesian cells define composites of horizontal morphisms. We'll use the Cartesian cells to then define formal Yoneda embeddings. So that formal notion will then recover the notion of sub-object classifier and also of Yoneda embedding. Then we'll end with some formal results that involve formal notions of size. So that's the plan. We'll start with looking at the notion of a sub-object classifier. Well, not quite that, but a generalization power object. But we'll take a simple case. We'll just look at power sets, so power objects in the category of sets. So a power set of a set A classifies relations from A into another set B. These are simply subsets of their Cartesian product. And it does that every such relation induces a unique map from B into the power set of A that I call J lambda. And at an element of B, J lambda of B is simply the pre-image of that element B under J, right? So all elements in A that are related in J to B. So by AGB, I simply mean the pair AB is contained in that relation J. So this J lambda is unique. How is it unique? Well, such that we can fill this triangle with a special kind of cell, and the left morphism on the left here is inclusion as singleton. So Y of an element A is just a singleton set of A in the power set. So we want to fill this with a cell chi. So to do that, we need to move up one dimension. We need to regard the power set as a partial order under subset inclusion. And then this cell chi is an equality of relations, the equality of J, and this subset relation on PA restricted on the left along Y and on the right along J lambda. So two elements A and B are related in J. if and only if A is in the pre-image of B. And that's the same as singleton of A is a subset of this J lambda B, and that gives us this inclusion. So chi exhibits J as the restriction of this subset relation along Y on the left and along J lambda on the right. So this will mean that chi is Cartesian. We'll make that precise later. And this will always happen. So when we have a triangular cell like this with object as a horizontal target, then that cell will always map into like the home relation or the unit relation at that object, right? That's what this subset relation is for PA. Okay, 2 notes here then. In Topos theory, this is generalized, these power sets, as the notion of power object. And secondly, if we restrict to the terminal set, like a singleton set, then what we get for Y is the sub-object classifier. So in that case, the power set of 1 will be the truth values, false and true, and Y is the inclusion of true in that power set. Right, so this is power objects, sub-object classifiers, and power sets. Now let's look at classical Yoneda embeddings. They form a similar universal property. So the category of presheaves on a locally small category A also classifies something. It classifies pro-functors from A to B. For me, those are functors from A up times B into small sets. So for each such pro-functor, there is a unique functor from B into a category of presheaves. Again, I denoted by J lambda. And J lambda of B, an object B in B, is J, but then with B fixed, right? So then you get the presheave on A. And here too, there's a Cartesian cell, chi, that exhibits J as, again, the restriction of this presheave category or of its home pro-functor along Y and J lambda. Now this is given by the Yoneda's lemma. So J at A and B is isomorphic to this home set of transformations between the presheaves, here the representable presheave, right? So Y here is the Yoneda embedding, right? I didn't tell you that. So this image is equal to this home set of transformations between presheaves. And that is exactly, again, this home set restricted on the left by Y and by J lambda on the right. So that is the same similar universal property as for power sets. Okay, so except that here J lambda is unique up to isomorphism. So some other things here. This presheave category might not be locally small, right? It's only locally small if A is essentially small. So in general, it will be locally large. And also B we can take to be locally large. That is okay. So we've seen these power sets and these Yoneda embeddings. They seem to have very similar universal properties. So our aim is a formal notion that unifies these two notions, right? And I won't really say what I mean by a formal notion here. I just mean an abstract notion that recovers both. Right. So let's look at the setting in which this formal notion lives. Well, first of all, it needs to be double dimensional, right? Both for the power object and for the Yoneda embedding, we have two types of morphisms. We have relations and profunctors. These we will draw horizontally, and we have functions between sets and functors. These we will draw vertically. So we need a double categorical setting. And then secondly, for these Yoneda embeddings, as I just noted, these pre-sheaf categories are likely to be locally large, and that has some consequences. First of all, profunctors with small sets as images might not compose at a locally large category, and also locally large categories won't have unit set profunctors, right? Their homsets might be large, so they won't form a small set profunctor. So we need a double categorical setting in which we cannot expect to have horizontal morphisms, and also we cannot expect to have horizontal units. And the natural setting is then that of augmented virtual double categories. So let me explain what those are. I'll first start with virtual double categories, those you might have heard of. So they were introduced by Baroni. So these are double categorical structures that you want to use if you do not have horizontal morphisms, but you do have horizontal units. That's when you use these. So they have four things. They have objects, vertical morphisms, horizontal morphisms, and then double cells whose horizontal source is a path of horizontal morphisms and whose horizontal target is a single horizontal morphism. So that's why I call them unary, because the target is a single horizontal morphism. And vertically, it has just two vertical morphisms. Now this horizontal source can be empty, and then you get a triangular cell like this on the right. Then we have composition in these virtual double categories of vertical morphisms, so they form a category. And also cells have this, alpharetic type of composition. And then we have identity morphisms for objects, and also identity cells for horizontal morphisms, and also identity cells for vertical morphisms. So that is the notion of virtual double category. Now let's look at augmented virtual double categories. So these you use when so virtual double categories you use when you do not have horizontal morphisms, but you do have horizontal units. I don't know if I said that correctly in the previous slides. For augmented virtual double categories, you use them when you don't have horizontal composites, and also you do not have horizontal units. So again, we have objects, two types of morphisms, unary cells, but now we also have nullary cells where the horizontal target is an empty path. It's just an object, right? So, and that includes cells like this on the right here, bottom right. I call these vertical cells where both the horizontal source and target are empty, right? So in particular, every augmented virtual double category has a two category of objects, vertical morphisms, and these vertical cells between them. A virtual double category doesn't have such a two category. It only does when it has all horizontal units. So, right. At first, I called these hyper-virtual double categories, but then Bob Paré suggested augmented, which is nicer, right? So yes, this notion of augmented virtual double categories is that of virtual double categories, but then augmented with these nullary cells, right? So that is, I'm happy with that term. So now we know the definition. Let's look at some examples. So these three examples are the ones that we'll use mostly. So we have augmented virtual double category proof of set pro functors between locally large categories, right? That's what we'll use to formalize the classical Yoneda embeddings in. Then we can restrict the size of the pro functors, and that allows us to only consider locally small categories. So by a small pro functor, J, we mean one for which if we fix an object in the target, then we get a small presheaf on A. That means it's a small colimit of representable presheaves. And the good thing about these small presheaves is that they do form a locally small category. So if we use small pro functors only, then we can use locally small categories instead of locally large categories. So S-prof is the augmented virtual double category of small pro functors and functors between locally small categories. Then to recover that power set notion, we use this, well, this is in fact a strict double category of modular relations between partially ordered sets and also their order preserving morphisms. And the relation is modular if it is compatible with the orders on its source and target like this. So that's the first three examples. Here we have some more, so we can also have internalized versions, so we can consider internal modular relations in a finitely complete category E. Then we get a modrel of E. So notice that we do not need E to be regular because we don't need modular relations to compose, right? So just having finite limits for E is enough to get augmented virtual double category. Similarly, we can internalize that proof example. We can consider internal discrete two-sided fibrations in a finitely complete two-category C. And again, we don't need the two-categorical analog of regularity for C. We don't need these vibrations to compose. So that's an advantage of working in augmented virtual double categories. So these are internal variants. Here we have the enriched variant of proof. If we have a universe enlargement of consisting of two monoidal categories, one contained into the other, and V prime should be large, complete, and co-complete, etc. Then you can look at V pro functors between V primed categories, right? V primed enriched categories. So if V is small sets and V primed is large sets, then this recovers the first example, proof. So we have internal enriched. We also have algebraic variants, monoproof of Lex monoidal set pro functors between locally large monoidal categories. So then we consider monoidal structure on the categories and the pro functors. Okay, so that's the definition and examples of augmented virtual double categories. Now, to give that notion of formal Yoneda embedding, we need the notion of Cartesian cell. So let me tell you about that. So here we have some cells in augmented virtual double categories. This by H underline, I mean a path of horizontal morphisms, H1 up to Hn, from x0 to xn. Now this cell psi here in the bottom right, we assume that its horizontal source is of length 1 or smaller. So it's either a single horizontal morphism or it's an empty path, then it's just an object. We call that psi Cartesian if it satisfies this universal property. So for every cell chi into the same horizontal target as psi and whose vertical boundaries factor through f and g, then the whole chi factors through psi as a cell phi. So if this horizontal source of psi is a single horizontal morphism, then we call that source the restriction of k along f and g, and we write k of f and g for j. And if we look at examples in set pro functors between large categories, then we do get restrictions like we would expect. So if this k underline is a single pro functor, then yes, k of f and g is simply k restricted along f and g. If instead k underline is an object, is an empty path, an object C, then that restriction of C along F and G is the same composite, except that instead of the pro functor, now we use the homsets of C. Well, these might be large, right? So they might up into a category of large sets. So this only gives us a set pro functor. It only gives us a horizontal morphism in prof if each of these homsets are small. And then lastly, if we set G the identity here, restrict to G being the identity, then we get the pro functor represented by F. So, and that only exists if F is what we call locally small. Each of these homsets are small. Right. So that's some examples in prof. Let's also look at examples in general augmented virtual double categories. So if we have a vertical morphism F, then we call it fully faithful is if it's the vertical identity cell for F is Cartesian, right? So that will be a vertical cell with empty horizontal source and target. That always exists. If that identity cell is Cartesian, then we call F fully faithful. F is called admissible if this restriction of its target along F exists. So that's what we call the companion of F. Like Bob also talked about that yesterday. So these two notions in prof, we recovered the usual notion of fully faithful functor and also of admissible functor, of locally small functor, right? As on the previous slide. And then an object in general, we call it admissible if its restriction of itself along the identity maps exists. And that horizontal morphism will be the horizontal unit of that object. So two remarks here for these notions of fully faithful and admissible vertical morphism. we don't need horizontal units of its source and target to exist. So if you would want to consider these notions in a virtual double category, then you do need these horizontal units to exist. And another thing, if you're used to virtual double categories, horizontal units there are usually defined using co-Cartesian cells. Here they are defined by a Cartesian cell. They can also be equivalently defined by a co-Cartesian cell. So in augmented virtual double categories, you can define them in both ways. They are equivalent. So that's restrictions and Cartesian cells. We'll also briefly use co-Cartesian cells at the end of the talk. Now we consider a cell phi in the top of the right-hand side, and we call it weakly unary co-Cartesian if any cell chi on the left factors through phi as a cell below phi, right? Unary co-Cartesian here because we restrict to cells chi that are unary, not ones that have an empty path at the bottom. And weakly because, well, there's also a stronger notion of co-Cartesian cell, but we won't use that here. We're mostly, we're interested in the case where phi has identities as vertical boundaries. Then we call J the horizontal composite of this path H. The weak unary composite of that path. So we'll use this later at the end. So because it's vertically dual to the Cartesian case, I wanted to tell you about it now. But yes, the Cartesian cells are the ones that we use for formal Yoneda morphisms, right? So they are morphisms because this definition won't imply that they are fully faithful. So I'll talk about that later. So a Yoneda morphism is a dense morphism. I won't tell you what dense means. Y from A into A hat that satisfies the Yoneda axiom for every horizontal morphism from the source of Y into B. There exists a unique, there exists just a Cartesian cell like this with on the right a vertical morphism, J lambda. And the density of Y implies that J lambda is the left Kahn extension of Y along J. So that means that any other vertical morphism with a Cartesian cell like this factors uniquely through this one as an isomorphism. That means that J lambda is unique up to isomorphism. So this recovers, well, up to equivalence because these pre-sheaf objects A hat are unique up to equivalence. In mod-rel modular relations between partial sets, we recover power sets. So A hat will be isomorphic to the power set of A with its partial order. Then internalized version in modular relations internal to some finitely complete category E, we get the power objects in E. So in fact, we get that mod-rel of E has all Yoneda morphisms if and only if E is a topos. Then in Prof, we get the classical Yoneda embeddings. Right, Prof is set Prof functors and functors between large categories. Then if we look at Lex-monoidal Prof functors instead, then we get we recover day convolution on that category of pre-sheaves. So that's the 4 examples. We'll see another example soon. So now let's pause and think about how our approach to formal Yoneda embeddings compares to a traditional two-categorical approach. So that is given by Yoneda structures on two categories, and then they were introduced by Ross Street and Walters. So these Yoneda structures consist of two things really. Firstly, they consist of a right ideal of admissible morphisms. So these formalize the notion of locally small functor, right? So they are the morphisms of the right size. Besides these admissible functors, they have Yoneda embeddings, formal Yoneda embeddings, Y, and they satisfy axiom similar to the Yoneda axiom on the previous slide. For every admissible morphism F coming out of the source of that Yoneda embedding, there exists a map from its target into this formal presheaf object, C of F1, and that is equipped with a cell that defines F as the absolute left lifting of Y along C of F1. So that's what the Yoneda structure is, these two things. Let's compare that to what we have. Well, for us, all horizontal morphisms are admissible, and then a vertical morphism is admissible if and only if its companion exists, right? And this Yoneda axiom is a bit simpler. It's simply that for all horizontal morphisms, we have a Cartesian cell like this. So, and an important point here is that, well, in a Yoneda structure, notion of admissibility is let's call it isolated, besides I being an ideal, right? So this class of morphisms is closed under precomposition with any morphism in C. But other than that, this notion is not related to other formal notions of two-categorical or formal category theory. On the other hand, for us, well, this companion is defined by a Cartesian cell, right? So for us, admissibility has to do with restrictions with Cartesian cells. So that means that our notion of admissibility is related to that of fully faithfulness, right? That also has to do with Cartesian cells. Also with adjunctions of adjoint vertical morphisms, and also restrictions of horizontal morphisms. So our notion of admissibility is a bit more inherent to the setting, and then that makes it more related to other notions, and that will be an advantage, as we will see. So lastly, these Yoneda structures also give us another example, a family of examples of formal Yoneda embeddings in our sense. Mark Weber has shown that if you have a two-tuple structure on a two-category, then that induces a Yoneda structure on that two-category. And the formal Yoneda embeddings that it consists of are, in fact, satisfy our notion of formal Yoneda embedding in this augmented virtual double category of two-sided discrete fibrations internal to this two-category C. So that gives us another family of examples of formal Yoneda embeddings. Right, then to conclude this talk, I have three results that involve some notion of smallness, two small results, and one a bit more sophisticated. So in the first result, we look at the small pre-sheaves again. So small pre-sheaves on the category A, let's denote it like this, set to the power A up with a little subscript s here for small pre-sheaves. Then you have this straightforward result that you can find in limits of small functors by day in LEC. It says it considers a functor f between locally small categories, and then considers the induced functor between small pre-sheaf categories given by left Kahn extending small pre-sheaves along F. So you can always do that functor that I've called F sharp always exists. Now the result is that F sharp admits a right adjoint if and only if this the set pro functor represented by F, right, that companion is a small pro functor, right? So at every C and C, object C and C, the pre-sheaf that we get on A is small. So in that case, this right adjoint is given by precomposition with F, but yes, precomposition with a functor doesn't usually preserve small pre-sheaves, right? I mean, the simplest example is when A is a discrete large category and C is the terminal category, then that won't work. So yes, that we have a right adjoint if and only if this companion exists in S-prof, in the augmented virtual double category of small pro functors. So let's consider the formalization of this result. So this F sharp, we need to get it as a pointwise left Kahn extension of this composite of F and the Yoneda embedding YC, right? So this, and then along the companion of the Yoneda embedding for A. So this we consider this pointwise left Kahn cell in any augmented virtual double category. And I don't have time to tell you what this means. So in S-prof, F sharp is the same as the one in the proposition. Well, let's consider these three conditions. The first one, F sharp, has a right adjoint. The second one, this composite on the left, is admissible, right? That means that its companion exists in the augmented virtual double category. And the last one, F itself, is admissible. So always B implies A holds for any augmented virtual double category. Under mild conditions, A and B are equivalent and C implies them. And under stronger conditions, which hold in this S-prof, right, of small pro functors between locally small categories, all three are equivalent, right? So in particular, we recover this classical result. So in Yoneda structures, you can also prove that B implies A, but I would be surprised if you can also prove the converse, that you can obtain admissibility because of that notion being isolated there, as I explained. So this is the first small formal result that involves notion of smallness, that admissibility, and the interesting thing is that we can also obtain admissibility, not only use it. Then the second small result, I already talked a bit about this. These Yoneda morphisms, their definition does not imply that they are fully faithful. Instead, that has to do with admissibility of of their source. So A is admissible if and only if both the restriction of A hat along Y on both sides exists and Y is fully faithful. So yes, that's what I talked about as well. This fully faithfulness has to do with admissibility. I don't know any example of a formal Yoneda morphism that is not fully faithful, but the definition doesn't imply it, and also there's quite a few formal results that don't use it, so I don't know. I mean, maybe it will be handy at some point. Then the last formal result, this is a bit more involved. So Weber proves the following theorem for Yoneda structures. If we have a formal Yoneda embedding in a Yoneda structure, Y from C into C hat, and C is small, that means that both C and C hat are admissible, and C hat is co-complete. And then Y defines C hat as the free co-completion of C. And the thing that's a bit funny here is that that you need to assume that C hat is co-complete for it to define for it to be the free co-completion of C. So we can improve on that a bit by choosing the right notion of smallness and also of co-completeness. What we do is we formalize a classical notion of street and freight. They prove that for any locally small category B, we have the following. B is essentially small. That means it is equivalent to a small category, if and only if its category of pre-sheaves is locally small. And then there's also, it's not hard to show that that is equivalent to a third condition, and that's saying that for any set pro functors H and J with B in the middle, the weak unary composite of them exists in this augmented virtual double category of set pro functors. Right, and these weak unary composites, I told you what they were. They had this universal property that was vertically dual to that of a restriction of, right? Defined by a co-Cartesian cell, vertically dual to a Cartesian cell. Okay, this last condition we formalize in any augmented virtual double category. So we call an object B weakly small if for any pair of horizontal morphisms with B in the middle, their weak unary composite exists. And then we call an object M weakly co-complete if the weak left Kahn extension of all pairs like this with B weakly small and D a vertical morphism into M exists. And again, I cannot tell you what these left Kahn extensions are. That it will be a morphism from a vertical morphism from E into M, right? So these two notions we use, so weakly smallness for an object and then weakly co-completeness for an object. And then we have the following theorem for augmented virtual double categories. If Y is a formal Yoneda embedding such that these restrictions of A hat along Y and any morphism, vertical morphism into A hat, such that they all exist, then the following are equivalent for any two objects, B and A. So for all pairs like this, a horizontal morphism between B and E and a vertical morphism into A hat, the weak left Kahn extension exists. That is equivalent to for all pairs of horizontal morphisms with the second one between B and E and the first one with source A, all these horizontal composites, well, these weak unary composites exist. So that is equivalent. Notice that this second condition, these composites existing, that is implied by B being weakly small, right? So the implication from left Kahn extensions to these composites, that gives us something of a size restriction on B, right? I mean, if all these composites exist, then B is weakly small. If these left Kahn extensions exist, then many of them will exist. Those with H starting at A, right? So these Kahn extensions existing is some kind of size restriction on B. And once more, if B is weakly small, then these composites all exist. So also all these Kahn extensions exist if B is weakly small. So in particular, this implies that this shows that A hat is weakly co-complete. So we don't need to assume co-completeness of pre-sheaf objects. We can obtain it if we choose smallness correctly. Now, we can also prove that A hat is the free co-completion of A under some mild conditions, but then it will be a bit more complicated again. Then we need pointwise left Kahn extensions, and they correspond to pointwise right unary composites. So I didn't want to go into that. I think that together with A being pointwise small, right, in this stronger sense, that will imply that Y defines A hat as the free co-completion in the stronger sense of A. So we can get a theorem like this for augmented virtual double categories as well. Right, so that's it. I hope I gave you a taste of formal category theory in double categories. Thanks for listening.
Amazing. Thank you so much for the talk. That's brilliant. So we have some time for questions now. Let me open up the floor if anyone wants to. Oh, sorry. People can just directly unmute themselves, or if you would like to raise your hands to ask a question, that's also fine. And maybe while we wait for a first question, I'd like to just ask a very naive question, which is, you define admissibility through like the existence of a companion, and it's just, is there like an interesting, is the dual story interesting? Like what happens when you study conjoints instead of companions?
Yes, I don't know if, I mean, it's just that I don't know. I mean, I guess with these with this Yoneda embedding, usually we talk about left Kahn extensions, right? So I guess the Yoneda embedding is usually on the left. So I guess that's why you work with companions then. I mean, that's the only thing I can think of it. I don't know. I guess yes. If you want to work in the horizontal dual of your category, then of your double category, then you might want to look at conjoints instead.
Okay, that makes sense. But yeah, I think it's because of Yoneda being where it is. Okay, we've got a question from Bob. Bob, would you like to ask your question?
Yes. So just a sort of a trivial question here. Well, very nice talk, just in passing. But you talked about various concepts being vertically dual, but you don't really have vertical duality in your augmented virtual categories, do you?
Yes, that's true. Yes, I think I also put mostly in front of it when I said vertically dual. So
Okay.
no, no, you're right. Of course, yes.
Okay, thanks. If anybody else has any other questions, they can unmute or raise their hands or even post them in the chat. I will read them out. Okay, if there are no other questions, then maybe we should thank Roald again for the lovely talk. Thank you.